Hello students, this worksheet is designed as the first review session for exam 2. We're going to review it in a reversed order. We'll review chapter 7 first in this worksheet, and the chapter 5 will be covered in a separate worksheet. And each worksheet will require more than one videos. Let's go to this worksheet, and here we're going to talk about mainly two topics: a power series method at an ordinary point, topic number 1, and a power series method at a regular singular point of type 1. There are different types of regular singular points, and of course there are irregular singular points. Basically, I'm going to throw all those out of the window because this is not a lesson. If this had been a lesson, I'll be covering pretty much everything, but this is a review session for the exams, so I'm going to focus upon two most important topics, two simplest topics rather. So ordinary point, number 1, and the regular singular point of type 1, that's number 2. Okay, ordinary point first. We already went through this kind of problem, this very problem by the way. Use the power series expansion at t equal to 0 to solve this given equation. Before going to this problem, let's take just a little bit of review. How do we tell this is an ordinary point? How do we know? We divide everything, each term, by the coefficient of the second derivative term. Then you're going to get this. Now let's take a look at each coefficient function. T over t minus 1, 1 over t minus 1. They are both analytic at t equals to 0. Yes, the denominator hits 0, but it hits 0 at t equals to 1, not 0. So at t equals to 0, this is okay. It's analytic. Differentiable infinitely many times, and it has Taylor series expansion, and we have appropriate interval of convergence. All good. But we already did this problem, so let's move on to the next topic here in this worksheet. And here we go. And is this really an ordinary point at t equal to 0? Divide everything by 1 plus t squared, the coefficient function for y double prime term. Now, is this coefficient function analytic at t equal to 0? And how about this one? The answer, yes and yes. As a matter of fact, the denominator never becomes 0 anywhere, so it's analytic everywhere. In any case, we have ordinary points at t equal to 0, and we can apply the power series method. Okay, let's begin. It's a long multi-step problem, and the step 1 is power series expansion. We begin with power series expansion given as this blue series. Y of t is summation and is going from 0 to infinity, cn t to the nth power. Taking the derivative of this term by term, we get the second series, the red series. N comes out and subtracting 1 from the power. Take the derivative again, then we get the green series, the second derivative. Now, subtle difference here, n is beginning from 1, n is beginning from 2, n is beginning from 1, so this is t to the 0th power, so we have the constant term and then up. N is 2 in this case, so this is again t to the 0th power, so we get constant function and up. But will this make difference starting from 1 versus starting from 0? The answer, no difference. Why? Think about that. Okay, we're going to come back to that issue in a due time. And let's go back to the problem. We have these power series expansions, and we're going to plug those into the original equation. We can put those into the original equation without any manipulation, and we can manipulate it later. Or we can break up parentheses first, and then plug in those series appropriately afterward. I decided to do the latter, so let's use the second form of the same equation, and I'm using the color coding: y double prime green, y prime red, and y blue. Now ready to substitute? Here's the result. the green series, the green series, the red series, blue series. All good. All these correspond to that. Okay, just a little bit of algebraic manipulation and we're going to be ready. This t squared times t to the n minus second power becomes t to the nth power. Next, this t times t to the n minus first power becomes t to the nth power. The result: second, third, and the fourth series are all in standard form with t to the nth power. The first series, that's a bit problematic and we have to do some work. In any case, that's the end of step 1. Let's review. Power series expansion, derivative and the second derivative, color coding help, original equation, plug them in, and a minimal algebraic expression, a minimal algebraic manipulation, t squared times t to the n minus second power yielding t to the nth power, t times t to the n minus first power yielding t to the nth power. That's where we are. Okay, let's move on to the second step, the index shifting. Please note that the second, third, and fourth series are all very good, t to the nth power. This one, on the other hand, is problematic, and we have to do some work, and that's the purpose of this index shifting. Okay, let's rewrite this expression that we got previously, but an additional color coding. I'm emphasizing the first series in brown because that's where the index shifting will take place. Again, why the first series? Second, third, and fourth series are all okay. We have t to the nth power. No problem there. Here we have t to the n minus second power. We need some work. Now I don't need this step 1 anymore, so let me minimize it and let's go from here. And let's work on the first series and let's do the index shifting. How do we make this one into t to the nth power? By replacing n by n plus 2. What am I talking about? Here we go. N plus 2 minus 2 so that this whole thing becomes n, and that's the purpose. We want this whole thing become t to the nth power. Now, I replaced n by n plus 2 here, so I have to do the same thing in all other n expressions as well. 1, 2, 3, 4 more of those. Here, n plus 2, n plus 2, n plus 2, n plus 2, and then of course n plus 2 here as well. If you do that, you're going to get the third series. T to the nth power, as we had before, and then n plus 2 is equal to 2, so the series begins from n equals to 0, and then the middle part, the coefficient, changed appropriately. N plus 2 times n plus 1 times c of n plus 2. So that's the end result of this n shifting. Now, okay, index shifting is done, but we need just a little bit more work here because second and third series are not complete because they don't begin from n equals to 0. Is that a problem? Yes and no. For ordinary points, no problem. For regular singular points, or even worse, irregular singular points, yes, those are going to be problems. Here, no problem. It's an easy fix. You can simply change this n equals to 2 and n equals to 1 into just all beginning from n equals to 0, like this. Please compare the bold green series and bold red series. They're the same. If you're interested in the reason, here it is. Compared with these two series, what's the difference? N equals to 0, then plug in n equals to 0 here, and we get the whole thing is 0. n equals to 1, then this whole thing is 0. Therefore, we have 0 plus 0, and then the rest of the series that begin from n equals to 2. Consequently, this and that are the same. About the red series, again the same idea. Plug in n equals to 0, then that's 0, and then the rest of the series begins from n equals to 1. Therefore, this and that are the same. So here is our conclusion up to step 2.